This time we're going to do just one problem, but I expect this problem to take up a decent amount of the board because it involves the merging of several concepts that we've studied throughout the entirety of this, and even borrows some information from algebra / pre-calculus. So if we have this integral here, this doesn't look anything like what we've seen in terms of the templates for inverse trig functions. We've usually seen some sort of a squared minus u squared or plus u squared or something like that, and square roots and things like that. But this doesn't look at all like what you might think of as a standard integral. And you might say, okay, well, I could try maybe u substitution. I could say u is the bottom here, but if I did that, it actually just doesn't work out. Like you want it to work out, and it just doesn't work out. So in these particular ones, we're going to have to be a little bit clever and use a skill that you may not have used in a while, but is a pretty important skill to, if you really want to start manipulating concepts in a meaningful way. And that's this idea of completing the square. So if you don't remember what completing the square is, what completing the square says is that I can take any second degree polynomial, and I can write it in this form. X minus h squared plus k. I can always rewrite it like this. And this is sort of that standard parabola form. Like you might remember that as the standard form of parabola. And the way that we do that is by completing the square. So what that tells me is that the algorithm to do this is pretty straightforward as long as the number in front is a 1. If it's not, you have to factor it out and do a couple of things. But if the number in front is a 1, it's pretty easy. What you do is you take so I'm going to do the complete the square piece in red here, and then we're going to finish the problem in blue. So the way you want to do this for completing the square is you say, you kind of take these first two pieces and you leave this one alone. The reason why you do this is that if you look at this formula here, it comes out to be x squared minus 2h plus h squared. And to do that, you'll notice that whatever's here, if you cut it in half, so if you divide this by 2 and square it, you get that term. So if you divide this by 2 and square it, you get that term. So what you do here is you do the same thing. You divide this by 2 and square it. This is xh. And then you have to leave off the x. So you take the coefficient, you take just this piece. So if that was like 10, for instance, you would take it, divided by 2 would be 5, and square it to get 25. And this could be negative or positive. In this case, it's positive. So if we divide this by 2, we get 1. If we square it, we get 1. Now here's the rub. We can't just add 1 for no reason, so we have to make sure that this new polynomial resolves to the old one. So if I take a look at this right here, everything I've done here still gets me back to my original one, right? Because those would dissolve and this would go to here. So we're not doing anything special. We're not inventing anything. We're just conveniently rearranging. So x squared plus 2x plus 1 minus 1 plus 5. So now we only want to analyze this piece. What this is a perfect square. This is x plus 1 squared. And this is 4. X plus 1 squared plus 4. So now again, you could totally distribute that out, use FOIL method, whatever you want, add this, and you'd get this back. What this has the added benefit of doing, though, is creating something that's kind of in that x squared plus a squared form. So if I go all the way down and I write this again, I get x minus 2 over x plus 1 squared plus 2 squared dx. So now I have something on the bottom that looks a whole lot like what we're thinking about using for the arctangent. However, nothing on top looks like I want for the arctangent, so I'm going to have to be even a little more clever here. So now I'm going to go and start doing this in blue to sort of show that we've moved past completing the square and have moved into the actual calculus portion. So the first thing we're going to do is we need to resolve this. We're going to take this to be u. We're going to say, all right, I'm going to let u be x plus 1, and du is going to be dx. Which is great because that's going to resolve this into u squared, and it's going to resolve that into du. But what do I do with this up top? That's not that helpful, right? So then what I'm going to have to do there is I'm going to have to say, that means x is u minus 1. And in particular, x minus 2 is u minus 3. Right, if I subtract 2 from both sides. So by doing that, I now have something to substitute in for each of those terms. So let's continue on over here. So I have u minus 3 over u squared plus 2 squared du. Which looks good and all, but we still haven't gotten rid of this. So this is where things get even more interesting. Now what we want to do is we're going to take this and split this into two integrals. We're going to say, okay. Now I just did a lot of work there, but all I really did was take the numerator, split it up, and then pull the negative 3 out here. I went ahead and turned that back into a 4, because why not? And then I left that as a 2 squared. Now what I want to do is I'm going to go ahead and solve this. We already know how to solve this. This is an arctangent template. Alright, so we just follow the arctangent template, kick this out. No sweat, no problem. We still have to deal with this though. And you're going, well, that doesn't look anything like these trig ones. They always have u squared plus something. It's always this like 1 on the top. There's never anything with a u on the top. And the answer is because this isn't an inverse trig problem. This is a standard u substitution problem. I have something squared plus 4, and then I have basically its derivative on top. So what I have to do here is I have to do a double substitution or an additional substitution. I've got to do something like w is u squared plus 4 and dw is 2u du. And since I have u du, let's divide both sides by 1/2. Okay. So because of that, this integral now becomes 1/2 dw over w minus 3/2 arctan. I just absorbed the negative 3 and 1/2 into a single term here. So I'm going to rewrite this a little bit. I'm going to pull the 1/2 out. Well, we recognize this, hopefully. 1 over something, d something. That's the natural log. So that's 1/2 the natural log of w minus 3/2 arctan u over 2 plus c. Okay, but then w is u squared plus 4 and I I took away the absolute value because this is always positive. But we didn't start in u's, we started in x's. So we have to go back to this original thing. U is equal to x plus 1. So this is 1/2 natural log x plus 1 squared plus 4. Now you could by the way multiply this out, because you could take this and recognize that it's equal to that, which is fine. You do whatever you want. Minus 3/2 arctan is 1/2 plus c. And lo and behold, it took us a whole board to do it. This is a big problem. And what this shows you, though, is that there's not just one simple technique that's going to solve your integral problems. You need to be familiar enough with the general ideas of the integrals and how to split them up so that you recognize when to apply the proper technique. If you take a look at this thing and just think to yourself, oh, use substitution, it's going to fail. But if you do all of this and you get here and you're just thinking, oh, well, it's just trig substitution, you're going to fail here. So this is not an easy problem, but I just want to emphasize to you that this is a really good example of needing to be well versed in the techniques of integration so that you can approach the problem confidently and competently.